Welcome to Power Up, a podcast show hosted by Maurizio Di Paolo Emilio that brings life to some of the stories on power electronics technologies and products featured on powerelectronicsnews.com and through other AspenCore media publications. In this show, you'll hear both engineers and executives discuss news, challenges, and opportunities for power electronics in markets such as automotive, industrial, and consumer. Here is your host, Editor-in-Chief of Power Electronics News and Embedded.com, Maurizio Di Paolo Emilio.
Hello everyone and welcome to this new episode of Power Up. Today the topic is diamond. We will talk about this new material and applications in terms of power electronics and quantum technology. So we are exploring the revolutionary potential of diamond-based semiconductor with Adam Quanta, founder and CEO of Diamond Quanta. From power electronics to quantum technologies, Adam's work is unlocking diamond's theoretical potential and making it a game changer in multiple industries. Adam is a pioneer in diamond semiconductor technology, renowned for his foresight and expertise. So let's talk with Adam. Hi Adam, thanks a lot for being here. How are you?
Doing well. Thank you so much for having me.
Thank you. Thanks a lot for your time. So Adam, where are you located?
Sure. I'm in the San Francisco Bay Area in California, United States.
Nice. So today, as I mentioned at the beginning, we will talk about diamond for power electronics, diamond for quantum technology. Before that, let's start talking about you. Please introduce yourself, give us a bit of your background.
Sure. So again, I'm Adam Quanta, the founder and CEO of Diamond Quanta. I've spent probably over 15 years now researching and developing various diamond technologies. Undergraduate studies, University of Illinois, Chicago in electrical engineering and physics, and graduate research at Stanford University, Stanford Nanofabrication Facility. Extensively, I've developed various diamond technologies varying from diamond growth and synthesis, from polycrystalline, nanocrystalline diamond materials, as well as single crystal, as well as optics, mechanical coatings, and semiconductor and quantum device work.
Great. So, Adam, let's talk about diamond. Diamond is often associated as the ultimate material for high power and high frequency applications due to its unique properties, features. So, however, its adoption has faced challenges, significant challenges. So, what makes diamond stand out compared to other materials such as silicon carbide and gallium nitride? And how is Diamond Quanta, your company, overcoming the traditional obstacles like defect, density, and doping?
Sure. Well, a lot of these other comparing materials have unique features over silicon. For example, gallium arsenide has very high mobility compared to silicon, but it doesn't have some of the other properties like the thermal conductance, like the minimization of materials with breakdown voltage. Diamond is very unique in that it is what's known as an all-around excellent performer. So diamond has the highest thermal conductivity of any 3D solid, has highest breakdown voltage of all the wide bandgap materials, so it requires the least amount, has very high drift velocity or saturation velocity, which makes it very good for a high frequency application use, high mobility, very fast switching, high power handling capability. So as a material of choice for these engineering applications, it really has many of these properties which make it quite favorable. In terms of the scale or the nascency, diamond, as I'm sure you know, really wasn't extensively developed until the early 2000s for chemical vapor deposition application. The other materials like silicon carbide, like gallium nitride, really started in the 1980s. So it's more of a historical lag over these two wide bandgap materials than anything else. But that being said, as you know, diamond can be made from any carbon-rich precursor. The molecule or gas of choice, of course, is methane. It being so abundant and being rather cheap to use. In terms of scalability, diamond is available today for polycrystalline for very large area application. Single crystal diamond, though, has been limited to date to about 4-inch or 100 millimeter due to the high stresses that are sort of inherent in that process. Silicon carbide, however, has very high processing temperature, typically 600 or 700 degrees Celsius, to be able to render the material. Diamond is known, at least in the polycrystalline side, to be able to be deposited at less than 500 degrees Celsius. So less of a seismic shift away from silicon processing and more consistent with the silicon processing standards in terms of the equipment set.
So, co-doping is at the heart of Diamond Quanta's breakthroughs. So, especially in improving charge, transport, and mobility. So, may you explain how your co-doping approach works and how it enables record-breaking electron and hole mobilities in diamond materials?
Certainly. So as I mentioned, diamond has been extensively developed for a number of decades, and a consistent problem has emerged in the doping of diamond. And that is every time, whether we're talking about in situ or in chamber doping or extrinsic via ion implantation, using a single dopant, the diamond lattice structure tends to relax into these graphitic-like interconnections and forming things like crystal pits or forming amorphous zones within the bulk material. This causes extensive scattering of charge transport carriers. And we really looked at this problem to understand, this being the major bottleneck, what is the unique problems in doping of the diamond? And we saw very extensively, both from theoretical and experimental reports, that there's a very specific geometric impact of doing the doping. The diamond lattice structure being anisotropic, have a preferred orientation. We saw that by adding these dopants, there were some localized geometric changes. So really extensively looking at the system, we sought to understand what are the roles of the intrinsic defects, like these dislocation or vacancy centers, and how do extrinsic defects like dopants affect the local order or local structuring? And putting this together, we came up with a co-doping approach, which deals with both the intrinsic and extrinsic defects inherent to the diamond structure. And we've tested this, as we mentioned, on both the polycrystalline, nanocrystalline, microcrystalline, as well as single crystal. And we're able to see a consistent trend in how these structures evolved post-doping. And the reports that we've been able to put out have showed a very high charge transport, high carrier mobility, low resistivity for all of these types of structures. So we see perhaps a very good solution that is applicable to all of the diamond types.
So, talking about applications, so the potential applications of diamond in power electronics are groundbreaking. So, from EV inverters to data centers, cooling, for example. So, how is Diamond Quanta positioning its technology to address practical challenges in industries like automotive and others, data centers? So, what efficiency gains can we expect?
Sure. So we're really focused on the design and the development of the doping structure itself. We have a number of partners for the diamond growth. We figure in terms of the expertise and focus, we want to focus on the semiconductor design itself. And many institutions today are working on diamond growth worldwide. And we have several of these partnerships that allow us to not focus on the diamond growth, to let others focus where their talents are, allowing us to bring in a material of high quality at very low cost. And then applying our doping, annealing, and device structure to these diamond types. This enables us to provide a breakthrough material and solution with increased performance, but at a very cost-competitive nature. So in this way, today, we're cheaper than gallium nitride-based technologies, which allows this material to really be deployed in these high-value applications. And as we talk about power inverter for automotive being a very high-temperature environment, data center also being very high-temperature environment, as well as aerospace and defense with jet engine and very harsh conditions requiring a very rugged material. And for these, we see diamond has exceptional value, I mean, even over silicon carbide, where silicon carbide and the like materials have bottleneck limitations of perhaps up to 400 degrees Celsius. Diamond can operate well over 600 degrees Celsius without performance degradation or breakdown. So it really is quite enabling for these type of applications. And we can expect that deploying diamond, particularly in automotive and data center, allows for a more compact profile, allows for lower system weights, reducing these cooling systems that are required on these systems, reducing the total system weight. And in the case of automotive, this means not only increased energy efficiency, but also increased range, because we reduce the weight of the system, allowing further range of the system with reduced weight.
Great. So beyond power electronics, Diamond is also showing great interest, promise in quantum technologies. So how does Diamond Quanta's work integrate quantum features, and what breakthroughs have you achieved in these areas like quantum sensing and compute?
So we've really focused on, again, the charge transport aspect of this application. What we've seen, particularly in deploying our codope structure in tandem or in conjunction with the color centers, that being either nitrogen or silicon in the case of diamond, is that we see very long coherence times in transporting the qubits across the bulk of our doped materials. This is quite enabling in that it increases the lifetimes of such interactions, which is a major bottleneck within these quantum systems. So we see that particularly in the case for quantum sensing, integrating our materials as the point of the electrical contact on the anode, or in the case of the N-type side on the cathode side, really allows us to work with such color centers and to be able to modulate them in a way that has not been done previously.
So with all these advancements, the scalability, adoption of Diamond technologies remain key questions. So you also mentioned something about cost. So looking forward, looking ahead, how do you see Diamond evolving in both power, semiconductors, and quantum technology? And also in particular, like my final question, what are the key challenges the industry needs to address to make this a mainstream reality?
So it's a very interesting time right now within the diamond community. So we've seen this huge boom in terms of the lab-grown diamond equipment, primarily from the gem side. And the gem had great success in that, you know, the cost of the diamond materials has really plummeted in the market, both for natural and from the gem side, just because it became so cheap to manufacture these materials. With countries like India and China, I mean, really scaling up, the market price of the diamond material has gone down considerably. And this has also led to an excessive capacity now in terms of this equipment. So the cost of the equipment itself to manufacture the diamond has come down. But outcome of this, which perhaps was not immediately foreseen, was the clustering and the large area capability of such systems now, enabling much larger area wafers of diamond to be produced. And so just in this last year, we've seen a number of the diamond equipment manufacturers come out with new systems which allow very large area and cluster tools to make it quite cheap to produce. So we're seeing now, in terms of the diamond foundry capability, that the diamond as a material choice is now more cost effective to integrate. The abundance of the equipment allows it to be deployed by fabs worldwide. And with the processes that Diamond Quanta is developing from the device side, as well as the other processes required with respect to things like packaging and other semiconductor processes, we see now a completed kit which allows a transition to the foundries to really start extensively developing and manufacturing these technologies. So in the next 5 to 7 years, we really do expect to see more of the major players, both on the defense side as well as on the traditional semiconductor foundry side, making investments into diamond, whether that be acquisition of other companies to bring in this expertise or developing it themselves. Another interesting point I wanted to mention was the governmental funding. So the U.S., of course, through CHIPS Act, has been producing or investing quite a bit into wide bandgap materials, diamond as well. Department of Defense and DARPA making substantial advancements in investments. as well as foreign counterparts making these investments. So the equivalent type of investments in China and the European zone into Diamond. So all of these things are needed to develop and stand up a Diamond ecosystem. And we could say, for the first time, really, since I've been involved in Diamond, seeing all these different players involved really gives a bright light at the end of the tunnel.
Great. So a great future for Diamond, for the next future. Thanks a lot, Adam. So stay in touch. Thanks a lot for joining us at Power Up podcast, and see you next. Thank you.
Thank you.
That brings us to the end of this episode. Stay tuned for more news and technical aspects about power electronics. If you are listening to this on the podcast page at eetimes.com or powerelectronicsnews.com, links to articles on topics we have discussed are shown on this page. Power Up is brought to you by Aspen Core Media. The host is Maurizio Di Paolo Emilio, and the producer is James Eade.